Hello, this is Mr. Taylor with Young Engineers Today. Tonight we are going to be talking about catapults. These are some of the materials that you're going to need this for the activities that we're going to be using while building catapults. It's alright if you don't have all these materials, and sometimes you just have to problem solve, hack, and engineer a different way of making these activities. You will also need the Mini Weapons of Mass Destruction Siege Weapons Book 3. As I stated, if you don't have all the materials from the previous slide, do not worry. The video from this webinar, which I'm recording currently, will be available for you to try to make the siege weapon anytime you like at your own pace. So, what is a catapult? The goal of a catapult is to fling a mass into the air, mainly to inflict damage. Catapults can be split into three categories: traditional catapults, ballista, and trebuchets. We'll be talking about trebuchets in a future webinar. For this, we'll be recapping ballista, which you can start hearing the word ballistic derives, and traditional. A traditional catapult looks like a bucket on a long arm being held down by some form of tension. A traditional catapult uses stored tension by twisting and stretching ropes and bending wood to vault its mass into the air. As you can see, by turning the rope and twisting it tightly, it builds up a large quantity of tension that is bundled here. The arm of your catapult that's attached to your bucket, it is put into this. And the tighter you get this, the further and larger amount of power is released. Wood and rope can do very well with tension, but to an extent. I mean, with anything, to an extent before it breaks. The energy stored in twisted ropes is similar to how energy is stored in a bowstring. A traditional catapult can store more energy to send their projectiles further by using a winch. A winch is a simple machine. It is a basic wheel and axle. As you can see here, the winch allows for the arm to be pulled back. If you make a mini catapult, a lot of times we just have like a trigger on it because we can pull it back ourselves. But the winch actually makes it easier for humans to pull back. Because right here you have so much tension built up, and you can see here they can latch this in and keep it tight, but you actually have a human. So you're giving this a mechanical advantage with the wheel and axle to pull this back. A winch allows a person to store a great amount of energy, in this case tension, over a period of time. Ballistas and other arrow shooting machines were the first catapults. A ballista looks like a giant crossbow, but as you can see with the wood and the rope here, you're once again using tension to launch this projectile, and they're using a winch here. Like a bucket catapult, a ballista works using tension stored in string and wood. You can think about a ballista working similar to a bow and arrow, but with additional energy stored in twisted ropes. History tells us that humans have limitations, and we all know this. We can only lift so much, can only throw so high, and we can only throw so far. So by increasing the energy stored in projectiles, you can increase the amount of damage that they will inflict. War has always been a motivating force in developing new technologies. This has helped engineers advance in many areas, not just weaponry. An example of this is that when World War II, a large quantity of resources went into creating the first nuclear bomb. A lot of that engineering, science, and math that was put into application helped derive nuclear energy, which we're still using today. On the other side of that, sometimes you get the flip. In the 1800s, we had basically dynamite was created, and it was used for civil engineering, mining, etc. Eventually that was turned into a weapon. So you have both sides of this taking place, but in most cases, war helps put a lot of resources into the advancement of engineering and technologies. So, gravitational potential energy. So, how can we increase the energy? The gravitational potential energy of an object can be found by multiplying the weight of the object, how high it is off the ground, basically weight times height. So, to increase the potential energy, not half but left, lift the projectile higher off the ground, make the projectile heavier. All right, so increasing its potential energy. Now, elastic potential energy of an object is determined by the material being stretched and how much the material is stretched. A lot of this falls under material science or material engineering because you're testing different materials, discovering what their elasticity is, their strength, as well as how they handle with potential energy, how they handle kinetic energy, how they feel being compressed. All right. Now, the history of catapults. Engineers research ways to increase these forms of energy stored in weapons in order to increase the damage. A lot of this is testing, materials testing, as we talked about. Now, in 399, a think tank to design and build weapons for a campaign against Carthage. Okay, so you're bringing a think tank is you're bringing all these extremely intelligent people, mathematicians, scientists, engineers, all these extremely bright individuals, and their goal is to overcome limitations of basic bow and arrow. So making new designs, testing new materials, looking at different ways of using it, and much more. This is a link below that allows you to interact with this archer and make discoveries. It's a game about angle and power. Which I want you to think about when you use this is what two factors does an archer have control over? Which one do you think affects elastic potential energy? And basically, the two factors you're going to come to conclusion are angle and power. And the one that can affect elastic potential energy is power, how far you pull back on that bow. And the link has been posted. A bow experiences compression on its concave side and tension on its convex side. Okay? Compression is this pushing and tension is this pulling force that you can see an example of this is your hands. So you get compression pushed together and tension is pulling. Now, how do these forces store energy? Imagine a loose rubber band, all right, versus a taut one. That taut one is going to have all this energy built up in it. That's potential energy. And when you let it go, it turns into kinetic energy. As I stated, potential energy is stored in a rubber band, just like how potential energy is stored in a bow and when a bow is drawn. Now, as you pull the string of bow, your arm does the work. The energy that it takes you to pull that string is stored in the bow as tension. Now, when arrow is released, elastic energy transfers the kinetic energy of the bow. Kinetic energy is energy that is stated as moving. All right. Now, the double skewer bow, you're going to build this. And you can find this in your booklet, your book, Mini Weapons of Mass Destruction, under the name double skewer bow. Now, some warnings. Always wear eye protection. Never substitute metal tableware for plastic. Never launch at people, animals, or things of value. Only use these at home. Ask for help using potential harmful tools like a knife, hot glue gun, wire cutter, or electric drill. Here are the supplies. 1 ballistic ballpoint pen, 2 wooden skewers, duct tape string, safety glasses, large scissors or hobby knife, 1 pen ink cartridge. That's inside the pink ballpoint tube. Now, if you don't have all of these, make do. As I said earlier, hack them, problem solve, make adjustments, make it work for you. Step 1, you're assembling the pen to various parts. If rear pen housing cap is too tough to loosen with just your fingers, use large scissors, a hobby knife, or pliers. Next, use scissors or knife to cut the pen housing in half. Save the ink cartridge for the arrow. Step 2, slide 1/2 of the pen casing you just cut over your 2 wooden skewers. Tape both ends of the pen housing so that it's centered along the skewers. Additionally, Add 2 pieces of tape to the end of the skewers, approximately 1/4 to 1 inch from the tips. Highly recommend measure twice, cut once. Now, depending on your skewer thickness and flexibility, you might only be able to use 1 skewer instead of 2. Step 3, now it's time to tie your string. This step is tough, so be patient. A pair of tweezers can be helpful if you have a hard time grasping your string. Tie one tip of your bow assembly with string, knotting the string several times and using the wedge-shaped gap between skewers to keep the string in place. Another thing you can do if it gets too loose, you can always put tape around the knot that you made at the ends. Slightly bend the bow and then tie the opposite using the same method. Trim extra string. You're going to have to experiment with how long to make that string, depending on how thick your skewers are, how flexible those are, as well as what type of string you're using. You can always substitute a string out with a rubber band. Okay. It's now time to fire. Remember, wear eye gear and do not aim at anything living. Center the ink cartridge arrow onto the pen handle, then grasp both the string and arrow slowly. Once the bow is drawn, aim and replace bowstring. Warning, if you are afraid, your ink cartridge may burst. You may use a coffee stirrer or skewer cut roughly the length of an ink cartridge. Now, you can also just tape the end of here and tape the end here of the ink cartridge so it doesn't leak out. Now, compression tension. The ability of a bow depends on its ability to store that energy. More energy stored translates to higher velocity of an arrow when released, which means more damage. So let's look at this chart. Shaded blue area under curve is stored energy. More energy stored means more damage. So if you look along the x-axis, how far you pull the bowstring back, you're noticing an increase in the stored energy. Okay, so as further you pull back your arm, that exerts, you're getting a larger stored energy. Now, as you get this increased draw length, okay, which is more than what you're putting in, so you're getting a mechanical advantage here. Now, there are some ways that people have advanced bows by shortening the string, by using different type of elasticity in the string. You notice that you get a larger stored elastic energy. Not huge, but pre-tension bowstring versus normal bowstrings, okay? Now, let's look at some other advancements, and you can see how you're getting more of this. Stiffer bow. So you can see how you can get a change, etc., okay? Now, this has led to compound bows that use pulleys and different materials, but what you're trying to do is get the highest mechanical advantage for your output divided by your input of what your arm is putting into it. Now, important limitations. Bows must be strong enough to carry the maximum pulling force without breaking. What does this mean in terms of improving design? We have to get to the point where it's efficient, it has a high mechanical advantage, but doesn't snap. Okay. Now, next class we'll start here at the compound bow. All right. Thank you, and this is Mr. Taylor with Young Engineers Today.